Hi everybody. In this talk, I'm going to present a new low-cost set CRDT. There are two families of CIDTs. We focus on state-based CIDTs. A classical example of CIDT is a row-only set, or known as the G set, where the states are sets, and these sets are ordered with the subset partial order. And between every two sets, a join of these sets exists, which is actually the union of these sets. So actually this gives us a join semi-lattice. In addition, if every operation, every update is inflationary, which means that the new state subsumes the old one in this subset ordering, then this will guarantee that every site can independently query and update its local states. And when all sites have applied the same set of updates, their states would converge. A grow-only set is limited in its functionality. We would like to have a general purpose set where we can both insert and remove elements from the set. The key issue with a general purpose set CIDT is how we are able to capture consistency and causality of different updates. So let's look at this scenario. We have three sites. Initially, they have the same states where the element A is not inserted at all. And from these equivalent states, if we apply the same operation, okay, the same update, then we come to the same states that are also equivalent as far as this element A is concerned. So from all these equivalent states, again, if we apply the same operation by removing the same element from these equivalent states, we achieve the same equivalent states again. Okay, so with this observation, we can try to represent the states of a single element in terms of equivalence classes of updates. For instance, if a single update has been applied to the state, we have a single equivalence class that consists of a single update event. If from this state we apply a removal update, we have now two equivalence classes. Each has a single update. Now consider site B sends its local state to site C. So this state consists of two updates, an insertion, an addition, and a removal. And when site C receives this state, it merges the two states by adding these remote updates into the corresponding equivalence classes. Okay, so then the state of a single element, it's updated in an inflationary way, in that we only add elements to new to equivalence classes or add new equivalence classes. So how do we decide if an element is in the set? We simply count the number of equivalence classes. If the number is an even number, then the element is not in the set. If it's an odd number, then the element is in the set. So in fact, we are only interested in the number of equivalence classes rather than the particular elements in these equivalent classes. And this number of equivalence classes, we call it causal length of this particular element. So this gives us to the design of new set CRDT, which is called CLSet, or causal length set. For every element, it's associated with a natural number. When this number is an odd number, this element is regarded as being in the set. For a local update, we simply increment this number by 1. For a merge, we compute the maximum of the causal length. Okay, so now let's compare CLSet with other existing set CRDTs. One of the most widely applied set CRDT is called observed remove set CRDT, or set CRDT, where every element is associated with 2 sets of dots. A dot is an identifier of an event. Typically, it consists of a unique set identifier and a sequence number that is unique at that site. So for all sets, for every element, it's associated with 2 dot sets. One is for the set of additions. The other is for the set of the additions that have been removed. The element is regarded to be in the set if there exists some addition that has not been removed. So compared to CLSet, we can see that all these states in all sets that are in the same shaded area, they actually have the same causal length. But do all set and CLSet have the same semantics? Actually, no. In fact, all set implements a semantics known as add-wins. And for an add-wins set, these states in red color, they have a different semantics as a CLSet. The main difference is that in add-win set, every single addition is regarded as different. So in a state where the removal only sees some of these additions, and if some additions still remains, then this element is regarded to be in the set. But in CLSet, some of these additions, they are regarded as equivalent. And removing one of these has the same effect as removing all of these. Another similar but different set semantics is known as the remove wins set, or RM set. For a remove wins set, these states in blue color, so these states have different semantics as add-win sets and different than also the CLSet. Of course, in a concurrent setting, all these 3 different set semantics could be regarded as acceptable. But we prefer the semantics of CLSet because in some sense, it neutralizes the add wins and remove wins semantics. We have also made some performance studies. Actually, we compared 3 different set CIDTs, the CLSet, the AllSet, and also an optimization of the AllSet known as the tombstone-free add-wins set. Our study shows that CLSet spent the least amount of time executing the updates and merges. It also uses the least amount of memory to perform these updates and merges. When performing queries that return the elements of a set, CLSet still outperforms the other set CIDTs most of the time. Only when a majority of the elements are deleted, so actually when more than 2/3 of the elements are deleted, in this case, the tombstone-free add-win set outperforms the other set CRDTs. To conclude, we presented a new set CRDT which has low cost because every element is only associated with a single number, which is known as the causal length. This single number still captures the causality and concurrency of addition and removal updates